Hey everyone, welcome back to another video. So today we're going to be going over the 2023 AP Physics 1 International Exam FRQ number 1. Right before we get into the solution for this, I did make some content review videos for energy, dynamics, kinematics, and soon the other topics like momentum, circular motion will be coming as well. So I'll leave a link to those videos below in case you're reviewing for the AP Physics 1 exam. But anyways, let's just get right into this FRQ. Alright, so it says student A and B conduct an experiment using a pendulum that consists of a metal spear that's attached to a lightweight string. So lightweight string, I would assume, means that this mass of the string is not negligible. That hangs from the ceiling as shown in the figure 1. The student displaces the pendulum a small angle from equilibrium and releases it from rest at time equals 0. So this is an example of a simple harmonic motion problem. So let's see what they want us to do. So the students create the following graph of the speed of the sphere. All right. The sphere first reaches the lowest point of its motion when the string is vertical at time t equals t1. Indicate time t1 by writing t1 in the appropriate box. All right, so this is when it first reaches, right? And the thing about simple harmonic motion is that it is a oscillating pendulum, and so it's going to repeat its motion multiple times. And you can see that the peaks of each of these speed graphs is the same, right? It's the same level, and that's because of conservation of energy. And so something you want to know about simple harmonic motion is that when it's at its lowest point, all of its energy from the gravitational potential energy is converted to kinetic energy. And when it's at its lowest point, that's also when it's going to be moving the fastest. All right, so we can see here that when it first reaches the lowest point, that is when it's going the fastest. So here, that lines up with box number 2, and so we can label that T1. All right, so the next thing says the students have a new pendulum. It's identical except the sphere has twice the mass. So let's circle that, twice the mass. And they plan the same experiment, yada, 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 at the same small angle. And they're trying to predict the speed of this new pendulum system versus the original experiment. So they have two predictions. So student A here thinks that the speed will be much greater, obviously in that same simple harmonic motion movement. Student B's prediction is that it's the original graph and nothing will change. So the answer here, let me just change colors, is student B. And this is because of conservation of energy. So let's just write the conservation of energy equation. Energy initial equals energy final. So if it's a pendulum released from rest, right, all the energy to start is just going to be mgh. Now that's equivalent to, we know at its lowest point, all of its energy gets converted to kinetic energy. So that's just kinetic energy equals 1/2 mv squared. What we can see here, interesting point, is that the masses cancel on both sides. And so it's irrelevant to our calculation for velocity. So here, if I were to solve for velocity, it would be 2gh square root of that equals v. All right? So that's why student B is correct. Alrighty, so for this next part of the problem, what they did is now they attached a spring. So attach a light spring to one side of the sphere, and they release it from rest at the same angle as before. And the spring is not in its equilibrium position. So here it's at equilibrium, but once they pull it, this is now being stretched. And so that now has spring potential energy. Just something to note here, and let's see what the question says. At time t equals 0, the sphere is released from rest. The sphere reaches the lowest point. The lowest point, we know that's where all of its energy is kinetic energy of its motion at t equals t2. Compare t equals t2 to the time at which the sphere reaches its lowest point in the previous part A. T1 is T2 greater than, less than, or equal to T1. So T1, let's remind ourselves, is this time right here. And this time right here. And we want to know what T2 is in comparison to that. So let's just write out what we know. So we know that T1 starts off with from rest. So it's mgh, conservation of energy, and that just goes to 1/2 mv squared. We talked about before, we solved for velocity. It was the square root of 2 times gravitational constant times height. But let's write out our scenario for T2, because now T2 has that extra pendulum. That extra spring, right? And so that extra spring brings in what we call spring potential energy. And so now we have both spring potential energy and gravitational potential energy. And something to note here is that this value and this value are the same, all right, because it's released from the same point. And so this is now equivalent to 1/2 mv squared. It's the same thing with kinetic energy as the only type of energy at the bottom. So if these two are the same, and we just add extra energy to it, that means we have a greater amount of kinetic energy. Let's switch colors. And so greater kinetic energy means greater velocity. And greater velocity means less time. And therefore, we know that T2 should be less than T1. All right, so now they want us to draw a single arrow that represents the direction of the instantaneous acceleration of the sphere. And this is for the center of mass at T2, so when it's at its lowest point. If the acceleration is 0, write a equals 0 next to the dot. So let's just draw our diagram. And we have our spring, and then our ball, and then that rope. So if we look at its motion, it's released from rest somewhere here. It'll go down, reach its equilibrium position, and sort of oscillates, right? So this is what its proposed motion looks like. So what we're looking at is right down here, what is the arrow that represents the direction of the instantaneous velocity? Well, when the ball or the sphere is released from here, you have that restoring force that's acting this way, right? It has to act to the left in order to get that sphere to go back down through its equilibrium position. But once it gets down here, it's actually going to swing back up. And so if its initial movement or direction is this way, then we know the instantaneous acceleration will have to be in another direction. Think about it through the lens of vector directions and stuff and vector components. So it's somewhere up like here, which allows the movement to be straight through and through the middle. And therefore, we can draw that instantaneous acceleration as just the arrow straight up. All right, so the final part of this problem says, after having passed its lowest point, the sphere continues moving toward the wall and momentarily comes to rest. At the moment when the sphere comes to rest, how does the magnitude of the angle the string makes with the vertical compared to the angle from which it was released? So simple harmonic motion here, we know that it's going to go back to the same angle. And why is this? Well, again, it's conservation of energy. So the amount of energy you have to start, we talked about before, was mgh, the gravitational potential energy, and then we also had the spring potential energy. So this is what we had to start. And so all of this we talked about as it reached its lowest point is converted to kinetic energy. So this is the lowest point. But once it reaches the other side, because it's oscillating, all that kinetic energy is now also converted back to mgh plus spring potential, because so this is final. If we look at this, let me scroll up. If it gets to a position that's here, right, and that spring is also going to be compressed. That spring, this is its equilibrium position. So if it's back here, that's being compressed, and so you're also going to have spring potential energy. Instead of now being stretched, it's being compressed. So that does it for today's video reviewing the 2023 AP Physics 1 International Exam FRQ number 1. Like I said before, make sure you check out the content reviews, and thank you for watching.